Hey, welcome back. We're in 2.1 now. This is linear inequalities in one variable. Right? So when we talk about inequalities, we're talking about expressions with one of these symbols, either less than, greater than, less than or equal to, or greater than or equal to. Right? So we're going to take a look at a couple of concepts dealing with this. The first, obviously, is simply the notion of less than. 1 is less than 4. That's true, right? 5 is greater than 3, right? So you should be able to have some sort of concept of greater than or less than at this point. So we're going to skip kind of those basics. We're going to move into actual expressions, inequalities that play with these. And we're going to kind of look back at, I think, section 1.2, I want to say, where we had our scale that was in balance. And if that scale is in balance, we have an equality. Right? But now we don't want our scale in balance, we want it out of balance, and we want to know what we can do with an expression when our scale is out of balance. So if that scale is out of balance, let me just redraw right here. Let's say we start out and we know we're not balanced. Right? This is an inequality. Now if I start out with an inequality, I know something's out of balance, I know one side is greater than the other side. Let's say I come over and add something to this side. Can I maintain that inequality? I don't know, because this other piece may equal it out, it may overcome the inequality, but the one thing I can guarantee is if I add something to this side to the right side and I add it also to the left side, I guarantee now that my inequality is going to stay unequal, right? And so we're kind of given, right, the addition principle in inequalities. That is to say that if I have some equality, and it doesn't matter which direction this equality is, it could be less than, it could be greater than, less than or equal to, greater than or equal to. If I have some inequality, and if I add something to both sides, as long as I add that same thing to both sides, then I'm guaranteed that same inequality. Right? And again, this could be greater than, if A is greater than B, then A plus C is greater than B plus C, and so on, right? So the addition principle is nice, it's given to us. C doesn't necessarily have to be adding something positive. I could come in here and cut something out of here and remove it, cut something out of here and remove it, right? It doesn't matter if I'm adding or removing, as long as I'm doing the same thing, then I'm good to go. And I can maintain my inequality. Right? However, well, let's take a look at this. Let's just see some examples of this. I have a true inequality, let's say 5 is less than 8, right? That's true. Right? But the addition principle says I can add whatever I want to both sides, and so I will. I'll come in here and say, let's add 10. Add 10 to the left-hand side, I have 15. I add 10 to the right-hand side, I have 18. 15 is still less than 18, so I maintain that inequality. Let's say instead of adding 10, I want to subtract 10. Then 5 minus 10 is negative 5. 8 minus 10 is negative 2. And negative 2 is greater than negative 5 because it's to the right on a number line, so I maintain that inequality. There's nothing I can add or subtract here that's going to make that inequality not true. Right? So that's the key. That's for the addition principle of inequalities. Let's take a look at the multiplication principle and see if that's also given to us. In fact, we'll start with that same one. 5 is less than 8, right? Let's assume for a minute that the multiplication principle is true, that I can multiply the left-hand side and the right-hand side by whatever I want. If that's true, then I can multiply, let's say, by 2. If I multiply by 2, 2 times 5 is 10, 2 times 8 is 16, and that still maintains that equality. So far so good, right? So good so far. But let's choose another number. Let's multiply this by, oh, I don't know, 100. Right? Well, 100 times 5 is 500. 100 times 8 is 800. And once again, that inequality is maintained, right? So I'm good. It appears to be that everything's okay, right? Let's try another number though. Let's just try, say, -1. -1 times 5 is -5. -1 times 8 is -8. But wait a minute. -5 on a number line is to the right of -8, which makes it larger. And my symbol switches directions to make this a true statement. So the inequality is not maintained here, and it's not maintained because I'm multiplying by a negative number, right? So that's our caveat here. When we're dealing with inequalities, we have to watch out for multiplying by negative numbers. And the same goes for division, right? If I were to instead have divided by -1, it doesn't matter. It's the same idea. Divide by -1, divide, or negative whatever you want. It doesn't matter. I still end up with -5 being greater than -8. So when I multiply or divide in an inequality by a negative number, I have to switch my sign. And that's the big caveat, right? That's the one thing that we have to be careful with. Everything else is pretty well fair game. Right? So let's take a look at a few problems like this. Let's say I have something fairly simple, right? X plus 12 is greater than 25. I want to find all x values that will satisfy this. And there's a lot. There's infinitely many, we'll see. But I can use the addition principle. It's free. I don't have to be careful. I can just subtract 12. I don't have to worry about the sign flipping on me. Addition principle is free. -12, -12. On the left-hand side, that just leaves me with the x. I don't have to be careful with my sign. It's just greater than still. 25 minus 12, 13, and that's it. All of the numbers greater than 13 will satisfy my original inequality. To graph this, right, graphically we're looking at start at 13. It's a strict greater, so it's open and everything to the right, right? In interval notation, that is a parenthesis at 13 off to infinity, right? 3 ways to write it. The fourth way was the set builder notation, which is x given that x is greater than 13, which is not a whole lot different than having simply stated that condition from the start, right? There's a freaking huge spider on the wall over there. Ugh. Sorry. Ugh. All right, let's take a look at another one. Spiders gotta learn too. All right, let's do, let's say 2x plus 1 is less than or equal to 15, right? So I'm going to solve this kind of the same way that I've been solving all of my equalities, right? I can still use my addition principle. The addition principle is free. I don't have to worry about signs, things like that. So this gives me 2x is less than or equal to 14. And I can still use my multiplication principle. If the number in front of my x is negative, I don't have to be careful, right? I can divide out my 2, my Symbol stays the same, so I get x is less than or equal to 7, right? And then you can turn that into the other types of answers if required to do so. But that's it. If I'm dividing by a positive, I don't have to worry about the sign changing. That's it, I'm good, I'm done. All right, let's take a look perhaps at say that, right? Did I go too far off the screen? No, I did not. All right. So I'm going to go through the same motions. I'm going to distribute my 4 through the negative 2 and then simplify. So I get 4x plus 8 minus 6x minus 2 is less than or equal to, because I haven't done anything yet, I still have that sign, less than or equal to 5x plus 2. Right? I can combine stuff on the left-hand side without messing up my inequality. So 4x minus 6x is negative 2x. 8 minus 2 is plus 6, less than or equal to 5x plus 2. Now I can use the addition principle for free. It doesn't matter what I'm adding or subtracting, and therefore I can subtract 5x from both sides without having to worry about the sign being changed. And since I'm dragging my x's to the left, I'm going to push this 6 off to the right by subtracting it from both sides in that same step. So that gives me minus 7x less than or equal to negative 4, right? But now when I want to isolate my x completely and get it all by itself, I have to divide by a negative. The 7 cancels, leaving me with just an x. This symbol though, I have to turn it. So this becomes greater than or equal to, and then the negatives cancel out here, and I'm just left with 4 7s. And that's it. That's my answer. That's the solution. I had to be careful here. So whenever you multiply or divide by that negative, be careful. Right? Switch that sign. Thanks, and I will see you next section.